Okay, in this last video of this particular little series here, we're going to look at getting those initial concentrations of the base and the conjugate acid, not by adding the conjugate acid in directly, but by converting it with a strong acid. A lot of times when people are looking at these things, they see ammonia and then hydrochloric acid, and like, well, how do I make a buffer out of that? Well, if you have a weak base and a strong acid, so that's the conversion method. You're never going to make a buffer directly with a strong acid, so you're using that strong thing to convert some of that weak thing into what you want to make. Usually, sometimes it ends up pretty close to, a 1-to-1 thing or a 50-50 kind of a thing. Not exactly, but it's close. So a couple of questions have come up recently about, well, what does the hydrochloric acid do? Why are you doing different tables? Why are you doing different things? Well, the reality is this strong acid isn't actually involved in the equilibrium at all. It's just taking some of this base and converting it into some conjugate acid before you do it, right? So all you had was base. You don't have any conjugate acid yet. So you're just going to take some of this and make this so that it will set up an equilibrium. Right, that turns out to be, again, if it's about a 50-50, close to 1-to-1, that's a pretty decent buffer. So making buffers this way often confuses people when you see it in a question. But if you see something weak with something strong and you see the words buffer in there, well, that means you're doing some conversion, right? Because you just can't make a buffer with something strong unless you're doing it, taking some of that weak thing and converting it into its conjugate. So what are a couple ways we can take a weak base and convert it over to some of it over to its conjugate acid using an acid? Well, it could be a solution of the weak base. Again, I'm going to use ammonia. So a solution of ammonia and a solid strong acid. Well, guess what? I've never seen that. So we're not going to do this. Right? Not saying it couldn't happen, but all of the strong acids that you guys typically see, hydrochloric, hydrobromic, hydroiodic, and nitric, all of these things are typically in the form of a concentrated solution and then diluted down to make a solution that you'd want to work with in a lab. I've never seen or worked with a strong acid that's actually a solid. So you shouldn't see that. If one comes up, bring it to our attention, but I don't think you'll ever see it. That saves a little bit of time. Nice. So usually in this method, and I've seen a few examples of this in the College Board questions, where they have the weak base, but then they give you a strong acid like hydrochloric acid. And this is where that question comes up. Well, how can you make a buffer out of this? Well, you can't directly. It's this hydrochloric acid is going to be giving its H+, 100% of its H pluses, to the ammonia to make some ammonium. Okay, so this weak base, strong acid, you're making a buffer through conversion. Something weak, something strong, you're converting. Okay, so to do that, with the converting, you can't really, it's not super easy to do just a simple dilution, even though it's two solutions. When you're doing conversions, when you're taking your ammonia and converting it into some ammonium, you got to know how many moles you're moving, and then we can figure out concentration from there. So let's figure out how many moles of each of these things are first. So if we're going to have 0.100 liters of 0.10 moles of ammonia per 1 liter. So that gives me what? 0.010 moles of ammonia. That's how much I put in there. Now we're going to convert some of that. But how much? Well, however much acid we put in there. So 0.050 liters. Okay, 0.050 liters of the hydrochloric acid, 0.10 molar, so 0.10 moles per liter of the hydrochloric acid, which means we're going to convert 0.0050 moles of that. So what do we have? we have 0.01 moles of ammonia, and we're to, we have no ammonium, which we need for a buffer. So we're going to convert it. We're going to use the hydrochloric acid to convert that. How much? 0.005 moles of it. So when we do that, how much ammonia do we end up with? How much do we have left over? Well, I had 0.01 moles of it. I converted 0.005. So I'm left with 0.005 moles of ammonia. I added these H pluses to that ammonia, to the original ammonia. How much did I convert over? Well, in this case, 0.0050 moles of it to make my ammonium. So what did I do? I had 0.050 moles of ammonia. I'm using hydrochloric acid to convert 0.005 moles of it. And then I'm left with 0.0050 moles of it, right? In this case, it happens to be sort of a 50-50, a 1-to-1 scenario, but it might not always work out just that nicely. The numbers might be slightly different. Okay, but I have 0.010 moles of ammonia. I'm converting 0.005 moles of it using hydrochloric acid by that H plus being given to that to make ammonium. So now I have 0.005 moles of ammonia and ammonium as well, but that's moles, not quite good enough. I need molarity. What is my new molarity? Well, I have moles, but I need to divide that by volume. What is that? That's 0.150 liters. That's the mixed value, okay? So what do I end up with? I end up with what? 0.033 molar ammonia to start my equilibrium table, right? And I actually have 0.033 molar then ammonium ion to plug into the other side in the conjugate acid side of my table. All right, so I converted 0.005 moles of it, of the ammonia. And then what's my new mixed value before it reaches equilibrium? So these are the initial values, 0.003 molar, right? Divide by the 150 milliliters there. So again, to review, this is the only way I've ever seen a strong acid actually added in, right? Used to convert a weak base. I've never seen strong acid in the form of a solid, only in a solution. But this version here, I've seen multiple times for sure in the College Board and may, in fact, come up in some of the homework questions.